This is part 3 of 8086 instruction set. We will see the in instruction. So in means we are taking input from a port, or we are going to read from a port. Okay, so the source of such an instruction will be a port address. So this is a sample in instruction format. Here we are going to do a 8-bit transfer from the port named 03 or addressed 03 to AL. Then if you are going to do a 16-bit transfer, right, or a word transfer, you have to use AX as destination. So for 8-bit transfer, AL is the destination which has to be used, and for 16-bit transfer, AX is the destination. Then one more thing, if the address of the port is not 8-bit, right, we have to move the address to DX and then use DX as source to indicate the port. So that is one restriction over here. But if the port is 8-bit addressed, then the port address can be directly specified as part of instruction. Okay, so that's what for 8-bit transfer destination will be AL, and for 16-bit transfer destination will be AX, and 16-bit port addresses has to be kept in DX and then used as source. Okay, so that's all about in instruction. Then out is used for outputting to port or writing something to port. So both in and out are actually IO instructions, port based IO instructions, right? Okay, so whatever rules applies to in also applies to out here. So if you are going to write a 8-bit data or value to a port, we have to use AL as source, and if you are going to write some 16-bit value, AX should be used as source. Then regarding the specification of address in the instruction, if the port is 8-bit addressed, that address can be directly specified in the instruction. But if the port is 16-bit addressed, what we need to do is that 16-bit address has to be moved to DX first, and then that DX can be used instead of the port in the instruction. Okay, so that's all about the out instruction. The next instruction is LEA or load effective address. So load effective address is actually used to get the offset, final calculated offset value of our source into a destination register. For example, suppose that ADR is a location within primary memory, maybe it's a label. So we need to know at what offset it is from its current segment register. Okay, so for that LEA can be used. So in such a case, the source should be the location whose offset we need to find, and destination is where we are going to write the offset value. Okay, so after the execution of this instruction, the offset of ADR within its target segment, maybe by default it is data segment, that offset will be copied to BX. Similarly, in this case, what happens is the offset will be calculated. This is an indexed mode, right? Indexed mode of addressing. So the offset within the target segment will be the sum of the contents of the BX register and whatever value ADR is holding. That sum will be the offset. So that offset will be finally moved to SI. Okay, so the load effective address means load the offset calculated offset value to the target register or the destination registers. Then we have two instructions together to be studied. It is LDS and LES. So it means load the pointer to DS or ES as the case may be. So usually LDS or LES is used in 8086 to load a far pointer value which is stored in primary memory. That is to load a far pointer stored in primary memory to a target register and the corresponding segment register. So suppose that this is a far pointer which is stored in primary memory. Okay, so the structure of far pointer in 8086 is the far pointer will first have the offset value, and it will have a segment that is a value to be populated into segment register. Okay, so far pointer is combination, that's a 32-bit pointer or an address which is combination of 16-bit offset value and 16-bit register segment register value. Okay, suppose that it is lying like this, that is the in bytes 5000 and 5001 you have the offset value, and in 5002 and 5003 you have the value to be put in the segment register. Okay, so suppose that you are issuing LDS BX comma 5000H. So we are just specifying the starting address of our offset value, right, or starting of our far pointer value, starting address of far pointer value, and executing this instruction. What happens is the first word from the starting location is treated as offset and it will be moved to bx. That's what you are seeing here. And the second word starting from this offset, right? So this is the first word. So second word is this word, that is word starting at 5002. That word will be treated as a segment address value and it will be moved to ds. Here it is, the instruction is LDS, so it will be moved to LDS. Suppose you are using LES, right? The only change here will be, because the target is bx itself, so only change will be the segment register value, right? Or the segment address value will be moved to ES, or the extra segment. Okay, so LDS and LDS is used to load a far pointer address stored in primary memory to a target register, right? Target register as well as a segment register. So that's what you need to understand from here. Then we have next set of instructions, that is LAHF and SAHF. Okay, so LAHF stands for we loading AH from the flags register, from the lower byte of flags register, and SAHF it stores the contents of AH to the lower byte of flags register. So their usage is just like this. They don't have any operands because all the operands are implicit. Because for LAHF you are loading the contents of lower byte contents of flags register to AH, right? So the source is the lower byte of flags register and destination is AH. So everything is implicitly understood, so it doesn't take any operands. Then similarly for SAHF, you are storing AH contents to the lower byte of F. So source will be AH and the destination will be lower byte of F. Okay, so as it happens, lower byte of F is our condition code. So you might be remembering that this is the flags register and this is its lower byte. So all the lower byte flags are our condition code flags. So effectively we are operating with the condition code portion of the flags register with these two instructions. So if you need to examine the condition code values at any instant of time, you can use LAH and see the contents in AH register. And suppose that you need to set the condition codes of the flags register, right? What you can do is whatever bits you need to set, you can make it as 1 in AH, and whatever bits you need to turn off, you can make it as 0 in AH. Then what happens? Then what you can do, you can issue SAHF. So whatever modifications you have done in AH or whatever settings you have done in AH, it will be copied to the lower byte of flags register, effectively resetting the condition code bits. Okay, so it is a very convenient way to deal with condition codes, that is to examine condition code and to alter condition codes. Now there are two instructions which deals with flags register and our stack. Those are PUSHF and POPF. PUSHF is used to push contents of the flags register, the entire contents of flags register into stack, as the instruction says. It's evident from the instruction. Then POPF is used to pop the contents from the stack, okay, which is effectively the flags register content back into the flags register content, flags register. Okay, so PUSHF does a normal push of flag into stack. So flags register, as we know, is a 16-bit register. So the MSB, right, or this section will be pushed first into stack, then the LSB section or the lower byte. Okay, so the higher byte will be pushed first, followed by the lower byte. Then regarding pop also, the reverse thing happens. First the lower byte will be popped, then the higher byte will be popped. So that's PUSHF and POPF. Again, it is different. The format is different from normal push and pop. In normal push and pop, we will have a register here, right? That is which register content has to be pushed, that will be specified over here. Then in pop also, the final the register to where the stack content has to be popped will be specified. But here everything is implicit, because PUSHF says that we need to push contents of flag register into stack. So the source of push is explicit here or implicit here within the instruction. Then in POPF, the final target to where we need to pop the current contents of stack is also listed, which is a flags register. So this is the usage format of PUSHF and POPF.